Even though this lesson is primarily on the first law of thermodynamics, there's a few things we got to get through first. For example, work. Work is classified as a scalar quantity, yet there is still a difference between positive and negative work. So let's go through this. And I'll use the example of me trying to lift up a box. When I lift an object, I'm performing positive work. And the reason is because work is equal to force times distance. I'm applying a force upwards and it's moving upwards. Gravity, on the other hand, it's performing negative work, because as the object is moving upwards, gravity is trying to fight by pulling it down. And because both of those are opposing directions, that's why the work due to gravity is negative. On the other hand, if I get tired of carrying this box and I allow the box to win me over, then I am performing negative work, because I'm still trying to apply a force upwards, however the box is winning. On the other hand, with regards to gravity, since the object is moving in favor of gravity, now gravity is performing positive work. Friction, on the other hand, always performs negative work. For example, if I try pulling the box towards the left, friction acts towards the right. And if I try pushing the box towards the right, friction will act towards the left. And since friction always opposes the direction of travel, that's why friction performs negative work. Before we advance forwards, I would like to redirect your attention to the two definitions at the top. Work is positive when work is done by the system onto its surroundings. An example of this would be a balloon filled up with gas, and let's say that that gas keeps on expanding. Well, now the balloon's able to bump into something, meaning that the balloon is capable of performing positive work. As for the second definition, where work is negative when work is done onto the system by its surroundings, imagine this. Let's say we have a tennis ball on the ground filled up with air. Some big person comes by and steps on the tennis ball. Even though that big person is performing positive work, the gas inside the tennis ball is performing negative work. A few more terms we need to cover. There's a difference between system and its surroundings. The system is the object that we're trying to measure. For our purposes today, we're talking about the gas that we're studying. And the surroundings would be the environment, keeping in mind that our environment right now is being crushed by atmospheric pressure. With the system that we're studying, it contains internal energy. Temperature is usually referred to as kinetic energy. Meanwhile, stored chemical energy, such as in gasoline, will be classified as the potential energy of that gas. Heat is a delta measurement. In other words, there needs to be a measurement of change. If there is no heat transferred between object A and object B, then the value of Q is equal to 0. There are two different types of boundaries, adiabatic walls and dithermal walls. Adiabatic walls do not let any heat escape. Meanwhile, dithermal walls are excellent at transferring the heat from the system into its surroundings. Even though there's no perfect adiabatic wall, a good example of it would be styrofoam. For example, if I pour hot water into a styrofoam cup, I don't necessarily feel the hot water in the cup. Same thing is true if I pour ice water into the cup. I still won't feel the temperature of the contents inside. On the other hand, if I use a metal cup, such as one from a pop can, if I fill it up with a cold beverage, I'll feel the results almost immediately. As you may have learned, there are only 3 laws of thermodynamics. However, since someone wanted to argue out a point and they didn't want to add a 4th law, they decided to call it the Zeroth Law, and this is what it says. Two systems are in thermal equilibrium if there is no net flow of heat between them when they are brought into thermal contact. Let's take a look at the pictures below. In the example on the left, we have 2 containers filled up with fluids that are at the same exact temperature. We take those 2 fluids and then we combine them together on the right. And if we observe what happens between A and B, the reality is there is no net energy transfer. Let's put it this way. Let's say you're trying to figure out the average of 2 grades. In one class you get 80%. In the second class you also get 80%. At the end of the day, your average is still 80%. There is no change. And that's what this law is trying to emphasize. You may have heard of the first law of thermodynamics like this. Energy cannot be created or destroyed, but can be transformed from one form to another. Or you may have heard of it this way. Total energy of an isolated system remains constant. But here's the truth of the first law of thermodynamics. Taking it that the total energy of an isolated system is constant, then any change in internal energy of a closed system is equal to the energy added by heat minus the work done by the system onto its surroundings. And here's what the formula looks like. I know this formula seems rather confusing, so how about I give you a visual example? Let's pretend that U is U, as in you with very deep pockets. Q is the warmth that you receive when your parents love you so much and they give you some money. And W is making that money work for you, as in used towards purchasing something at a store. And that's why you'll lose some of the money. Now, it is very possible for the opposite to occur as well. For example, let's say that person at the store is your boss, and they pay you money, and then you pocket that money. Well, now you'll notice that the direction of work changes, and you end up getting a double negative, so now you gain money. On the other hand, if you so happen to break the dishes in the house, and your parents are upset with you, they may take away a portion of your allowance to pay for it, along with that warm, fuzzy feeling of love. So that's what this formula actually means. Any change in energy in you is based upon whatever heat that you have minus any work that you do onto the surroundings. Now that we have a general idea of this formula, let's properly define Q and W. Q is for the quantity of heat given to the system. So when you gain heat, Q is positive, and when you lose heat, Q is negative. W, on the other hand, is the work that the system does onto its environment. So just like when you exercise, you get tired and you lose energy, when you perform positive work, you end up losing internal energy, and that's why there's a minus sign in the formula. On the other hand, it is possible for you to perform negative work, and a classic example is a gas being compressed by its surroundings. So what you end up getting is negative work due to the work done by the surroundings onto the system, and the formula has another minus sign. So you end up getting a double negative or a positive value at the end of the day. I know that this seems confusing, but if you actually look at the original formula, that's even more confusing. So for our purposes here, let's stick with the AP version, which is a simpler one on the left. Let's say that we have 1800 joules of work done onto the system by its surroundings, and an additional 2500 joules of heat is also added to the system. What is the change in internal energy of this system? First, the work that we have here is negative work, and it's because it's work done onto the system by its surroundings. If this sounds confusing, here's an example. Let's say I have a container filled up with gas, and there's a piston that's able to compress the gas. Take a look at the motion of the gas right now, and take a look at the motion of the gas afterwards. You can visualize this as if you're sitting in a busy bus, and the bus driver suddenly forces more people to come in. You bounce back and forth with other people, and you end up gaining more kinetic energy. So whenever you compress a gas, you actually gain more internal energy. Number two, let's say you so happen to add heat into the system as well. Now you have the sum of those two values of internal energy. So you have 2500 joules minus negative 1800 joules because it's work done by the surroundings onto the system, and that double negative becomes positive. So at the end of the day, you gain a whole lot of internal energy. Here's another conceptual problem. In case A, you have a system that gains heat, but it loses energy because it's doing work onto its surroundings. In case B, you have a system that gains heat, but also gains energy from the surroundings. And here are the numbers that go along with it. Just to let you know, on an AP exam, often you're given more multiple choice questions than you have the time to solve it. So with problems like this, it's actually more efficient to try to figure out what the answer should be than it is to pull out a calculator and calculate it out. So let's go through this problem without a calculator. In case A, the system gains 1500 joules of heat from its surroundings, and it loses 2200 joules of work because it's doing work onto its surroundings. So you gain 1500 and you lose 2200. Obviously, you're going to have a negative answer, and if you look at the multiple choice without a calculator, you know that you're left with choice A, and that actually is the correct answer. Let's go through the second one as well. In part B, the system also gains 1500 joules of heat, but 2200 joules of work is done on the system by its surroundings. In other words, the outside universe is giving more energy to you. So you start off with 1500, another 2200 is given to you from the outside universe, so you know that you will gain even more energy. Looking on the left, you know obviously you're going to have an answer greater than 2200 joules. So E would be the correct answer. And that's how you'd solve these type of problems much more efficiently on the AP exam. Here's a more involved mathematical problem. The temperature of 3 moles of gas is reduced from 540 Kelvin down to 350 Kelvin by two different methods. In the first method, 1500 joules of heat flows into the gas, whereas in the second, 1500 joules of heat is removed. A, find the change in internal energy, and B, find the work done by the gas onto its environment. On the AP exam, you'll be given the following equations on the right. First, we need to solve for the change in internal energy. And since delta U is equal to U2 minus U1, that means that delta U is also equal to 3 over 2 nRT2 minus 3 over 2 nRT1. Optionally, you can factor out 3 over 2 nR and solve for the difference in temperature. In fact, this is the method that I would recommend you in solving it, as it reduces computational error. When it all works out, again, as we said, it's going to lose energy, so we would expect a negative value. Next, we're trying to find out the value of W, the work of the gas onto its surroundings. So we isolate for W and we sub in all of our knowns. In either case, you'll notice that you end up with quantities that are positive, meaning that work is done by the system onto its surroundings. How about one more question? A gas is enclosed within a chamber that is fitted with a frictionless piston. The piston is then pushed in, thereby compressing the gas. Which statement below regarding this process is consistent with the first law of thermodynamics? Is it A, the internal energy of the gas will increase, or B, the internal energy of the gas will decrease, or is it C, there's no change in internal energy, or is it D, the internal energy of the gas may go up, may go down, or may remain the same depending upon the amount of heat that the gas gains or loses? And the answer is actually D. And the reason why the answer is D is because it hasn't been provided for you what type of wall you have. Was the wall adiabatic or was it dithermal? After all, if the wall was adiabatic, then the internal energy would increase. Anytime you compress a gas, it will gain heat. And if you don't let the heat escape, then the internal energy will go up. On the other hand, if you compress a gas and it heats up, but because you have metal walls and the heat's able to escape, then yes, you could have the possibility of case B. And that's why the internal energy may go up, go down, or maybe even net to a neutral value. It just depends on the scenario. For more additional questions, work on the following homework questions, or work on these questions over here. Until our next adventure together, have fun!